Assalamualaikum and greetings to everyone. We are from Group 3 and we will be presenting the accounting theory and emerging issues in regard to the new technology which are cloud computing and big data.
So what is cloud computing? Cloud computing is the delivery of computer services including servers, storage, databases, networking, software, analytics, and intelligence over the internet to offer faster innovation, flexible resources, and economies of scale. It allows users to access technology services on an as-needed basis from a cloud provider by eliminating the need for purchasing, operating, and maintaining on-premises physical data centers and services. It can be private, community, public, or a hybrid, and it can be accessed from any internet-capable device. Cloud infrastructure involves the hardware and software components required for the proper functioning of cloud computing, and it is used by organizations of every type, size, and industry for a wide variety of use cases such as data backup, disaster recovery, email, virtual desktop, software development and testing, big data analytics, and customer-facing web applications.
So as you can see from the first picture, this is how cloud computing actually works. So for the second picture is a list of some top cloud providers that are well known nowadays in the world.
So there are 4 types of cloud computing, which is the first one is private, public, community, and hybrid. So the first one is private cloud computing, which refers to a cloud environment dedicated to a single organization, providing many of the benefits of public cloud such as scalability and elasticity while offering additional control and customization. It can be hosted on premises at a third-party colocation facility or by a private cloud provider. It is a single-tenant environment, which means that all resources are accessible to one customer only, providing a higher level of security and privacy. It can be managed by the customer or outsourced partially or fully. It is commonly used in industry with high security and compliance requirements such as healthcare and finance. So the second one is public cloud computing, which refers to cloud services provided over the internet to the general public without being dedicated to a specific organization. In public cloud, resources are shared among multiple users, which allows for faster and more efficient allocation of resources. There are 3 types of public cloud services, which is the first one, infrastructure as a service, which provides virtualized computing resources such as servers, storage, and networking, which allows users to run IT infrastructure on demand. Second one is platform as a service, which offers a development platform for creating and deploying applications with tools and services provided over the internet. The third one is software as a service, which delivers applications over the internet, allowing users to access and use software without installing it in their device. The third one is hybrid cloud computing, where it combines a private cloud and a public cloud, allowing data and applications to be shared between them. This type of cloud environment provides a greater flexibility and more deployment options, enabling organizations to optimize their existing infrastructure while leveraging the public cloud for specific needs such as scalability and cost efficiency. By using a hybrid cloud approach, businesses can keep sensitive data and critical applications on premises while taking advantage of the public cloud's resources for non-sensitive operations. The last one is community cloud computing. This is where multiple organizations pool their resources and expertise to create a shared cloud environment. This model is often used by organizations with common interests in a specific domain or industry, such as scientific research or financial services, to calibrate and leverage the power of cloud computing together. In a community cloud, the participants contribute their resources and capabilities to the cloud infrastructure, which can be accessed and used by all members for various purposes, such as data storage, processing, and application development.
Now, let's jump to the rationale and origins of cloud computing. The origin of ideas related to cloud computing can actually be traced back to around 1950s. Companies started using large mainframe computers, but due to the expense, not every organization could afford to purchase one. So, during the late 90s and early 1960s, a process called time sharing was developed to make more efficient use of expensive processor time on the central mainframe. Time sharing lets users access numerous instances of competing mainframes simultaneously, maximizing processing power and minimizing downtime. This idea represents the first use of shared computing resources and the foundation of the modern cloud computing. Next, the origins of delivering computing resources using a global network for the most part rooted in the 1969 when American computer scientist Lee Clyder helped create the Advanced Research Project Agency network. His goal was to connect computers across the globe in a way that would let users access programs and information from any location. In the 1970s, cloud computing began to take a more tangible shape with the introduction of the first virtual machines, letting users run more than one computing system within a single physical setup. This functionality of these virtual machines led to the concept of visualization, which had a major influence on the progress of cloud computing. Around the time of 1970s and 1980s, Microsoft, Apple, and IBM developed technologies that enhanced the cloud environment and advanced the use of cloud server and server hosting, while in 1999, Salesforce became the first company to deliver business applications from a website. In 2006, to be specific, Amazon launched AWS, providing services like computing and storage in the cloud. Following suit, the other major technology players, including Microsoft and Google, launched their cloud offerings to compete with AWS. Microsoft launched Azure in 2010 and Office 365 in 2011. Also, the Docker container technology was first released in this decade. Microservices and serverless platforms were also introduced in this timeframe when the Google App Engine was launched in 2008, followed by AWS Lambda in 2015. As of today, the growth of serverless computing is anticipated to continue and edge computing will become more and more significant in the upcoming years. Edge computing devices are expected to improve and become more interconnected as AI and machine learning technologies. I will delve into the factors that have significantly contributed to the development and widespread adoption of cloud computing. The first key factor is scalability. Traditional on-premises infrastructure often struggle to meet the challenges of scaling up or down in response to fluctuating demand. Cloud computing has changed the game by offering dynamic scaling capabilities, allowing organizations to easily expand or shrink their computing resources based on their specific needs. This flexibility provides a level of agility that was previously unattainable. Next up, we have cost management. Establishing and maintaining on-premises data centers involves substantial upfront capital investments and ongoing operational costs. Cloud computing offers a pay-as-you-go model, allowing organizations to pay only for the resources they use, which can result in cost saving. Now, let's talk about resource utilization. Traditional data centers often suffer from inefficient resource utilization, with servers running at low capacity. Cloud providers address this challenge by optimizing resource utilization through hosting multiple tenants on the same physical infrastructure. This approach enhances overall efficiency, ensuring that computing resources are utilized to their full potential. Moving on to the data redundancy and backup. Ensuring data redundancy and implementing robust backup strategies are critical for business continuity. Cloud providers offer geographically distributed data centers, automated backup solutions, and disaster recovery options. This feature makes it easier for organizations to protect their data and providing a secure and reliable environment. Last but not least, we have rapid deployment. Traditional infrastructure provisioning processes could be time-consuming. Cloud computing streamlines this by enabling rapid deployment of resources, significantly reducing the time it takes to launch applications and services. This increased speed contributes to faster innovation cycles and quicker time to market for businesses.
My name is Nur Atika Ayuni binti Zaini, and I will proceed with the characteristic of cloud computing. The first characteristic of cloud computing is resource pooling. Public cloud providers rely on multi-tenant architectures to accommodate more users at the same time. Customers' workloads are abstracted from the hardware and underlying software, which serve multiple customers on the same host. Cloud providers increasingly rely on custom hardware and abstraction layers to improve security and speed users' access to resources. Another essential cloud computing characteristic is broad network access. You can access cloud service over the network and on portable devices like mobile phones, tablets, laptops, and desktop computers. A public cloud uses the internet while a private cloud uses a local network. Latency and bandwidth both play a major role in a cloud computing and broad network access as they affect the quality of service. Data security is one of the best characteristics of cloud computing. Cloud service create a copy of data that is thought to prevent any form of data loss. If one server lost the data by any chance, the copy version is restored from the other server. This feature comes in handy when several users work on a particular file in real time and a file suddenly gets corrupted. However, the responsibility for security is shared between the provider and the customer. Traditional computing and modern cloud computing differ in various aspects. The first aspect is the infrastructure ownership. Traditional computing involves owning and maintaining physical hardware, including servers, storage, and networking equipment, while modern cloud computing relies on shared infrastructure provided by cloud service providers, which will eliminate the need for organizations to own and manage physical hardware. Next aspect is cost model. Traditional computing typically involves upfront capital expenses for hardware and ongoing operational expenses for maintenance, while modern cloud computing adopts a pay-as-you-go or subscription-based model where users pay for actual usage, promoting cost efficiency and flexibility. The last aspect is scalability. Scaling requires purchasing and configuring additional hardware, which can be time-consuming and expensive for the traditional computing, while modern cloud computing provides rapid elasticity which allow for automatic scaling of resources up or down based on demand.
Assalamualaikum, my name is Nur Ilya Maizurin. I will proceed with the advantages of cloud computing to the accounting profession. So there are 3 advantages which are enhancing security, data backups, and it could reduce the paperwork. So cloud computing is to ensure that the security and the integrity of a client data by reducing the possibility of a data leak of a computer hacking. It could be reduced by using the encryptions and the multi-factor authentications. So the second one is authentication or data backups, where cloud computing enables accountants to focus on their critical work and become more efficient. So lastly, cloud computing could reduce the paperwork. With cloud computing, accounting can significantly reduce the reliance on paperwork because they email invoice to clients, eliminating the printings and the postage. We continue with the cons or disadvantages of cloud computing to the accounting profession. So cloud computing is too dependent on the internet. There are limited customization and would create an ongoing cost. So first, a cloud computing is a dependency on the internet where any disruption or outages can affect the access to the critical financial data, and it could delays in accounting processes. And they also would create an ongoing cost. Could be a hidden cost such as the transfer fees, additional storage costs, and potentially impacting the budget of accounting firms. And lastly, cloud computing has a limited customization. Cloud accounting software may not provide the same level of customization as a locally installed solutions, restricting the ability to tailor the software.
So, we use an example from Deloitte to be our case-based solution. As more companies move to or grow their multi-cloud environments, they will face one common challenge, which is how to upskill their employees on core concepts in an efficient way. For one global financial institution, doing so was even more of a challenge since employees all over the world needed to learn core concepts that would ultimately accelerate cloud adoption regardless of the cloud service provider, which is known as CSP. The company understood the benefits of a multi-cloud strategy but needed help from Deloitte to rapidly upskill its employees, to use its current CSP, as well as to create a solid foundation that other CSPs could build upon. That meant creating learning content for open source tools alongside CSP-specific products. Part of that process required developing personas, which are a high-level description of each employee role, such as required certifications and also technical skills, in order to help structure those pathways, not just for employees currently in the role, but for all of those who may have the role in the future. One of the challenges the company faced was cohesion. With multiple brands operating under the parent organization, each company had different views of each persona, which created barriers to streamlining both the immediate and future learning processes. To move the organization to the cloud meant developing a common language for all the roles within each brand.
For the solution, Deloitte first performed an assessment to determine learning needs of each of the groups that will be migrating to the new cloud environment. The process involved identifying gaps in skills and learning materials and creating 60 personas, such as cloud architect and cloud financial analyst, that will be extended throughout the organization by orchestrating communication among all divisions of the company to find common agreement. From there, Deloitte coordinates and launches rapid upskilling for priority groups through bootcamps and various training opportunities that were at the beginning, intermediate, and advanced levels. The approach was unique because of the Deloitte's business relationship with its current cloud service provider. That gave Deloitte additional training support, which quickened the process and increased the participation rate. Both the design of the rapid learning sessions and the learning pathways content created by Deloitte were made to be repeatable for the organization to use as it continued its cloud journey. Ultimately, what Deloitte created was a framework for upskilling talent, regardless of the CSP. The pathway process were purposely durable, so the organization could build upon it into the future.
Next, we will proceed with the big data. Big data is a data set that are too large or too complex to be dealt by traditional data processing application software. Data with many entries offer a greater power, while data with higher complexity may lead to the higher false discovery rate. Big data can provide a company with all the necessary insight to develop new and innovative ideas for product or services, or even their marketing campaign.
As the internet age continues to grow, we generate an incomprehensible amount of data every second. This data can be classified according to the following types, which are structured, unstructured, and semi-structured data. So firstly, structured data is a highly organized type of data and has certain predefined organizational properties. It is presented in structured or tabular schema, making it easier to analyze and sort. A database of customers' information would be one of the examples of structured data. Moreover, due to its predefined nature, each field is discrete and can be accessed separately or jointly along with data from other fields. This makes structured data extremely valuable, making it possible to collect data from various locations in the database quickly. Next, unstructured data entails information with no predefined conceptual definitions and is not easily interpreted or analyzed by standard database or data models. Unstructured data accounts for the majority of big data and comprises information such as dates, numbers, and facts. Big data examples of this type include video and audio files and mobile activity. Photos we upload on Facebook or Instagram, and videos that we watch on YouTube or any other platform contribute to the growing pile of unstructured data. Last but not least, semi-structured data is a hybrid of structured and unstructured data. This means that it inherits a few characteristics of structured data, but nonetheless contains information that fails to have a definite structure and does not conform with relational database or formal structure of data models. For instance, JSON and XML are typical examples of semi-structured data.
The history of big data can be traced back to the early days of computing, but the concept gained prominence and evolved significantly in recent decades. In the early days of computing, which is 1960s to 1980s, data storage and processing were limited by the capacity of mainframe computers. Databases such as IBM's Information Management System and the relational database model introduced by Eja F. Code in 1970 laid the groundwork for structured data management. Next, the emergence of data warehousing and business intelligence system in 1990s allowed organizations to store and analyze large volume of structured data. Technologies like online analytical processing and data mining gained popularity during this period. The advent of the internet and the growth of Web 2.0 in 2000s led to an explosion of unstructured data, including social media content, emails, and multimedia. Google's introduction of MapReduce in 2004 and the development of the header developed framework in 2005 by Yahoo engineers Doc Cutting and Mike Caffarella marked a significant shift in processing large-scale distributed data. In 2008, Big Data term coined. The term Big Data gained prominence when O'Reilly Media organized the first Strata conference on Big Data in 2011. Big Data was defined by the three V's, which are volume, velocity, and variety. Big data technologies maturation happened in 2010, where Apache Hadoop became a popular open source framework for distributed storage and processing of big data. NoSQL database emerged as an alternative to traditional relational database, which will provide flexibility for handling diverse data types. Cloud computing platforms such as Amazon Web Service and Microsoft Azure play a crucial role in providing scalable infrastructure for big data analytics. The integration of machine learning and advanced analytics with big data allow organizations to derive meaningful insights and prediction from large data sets. Technologies like Apache Spark, designed for in-memory data processing, gain popularity for faster analytics. Big data continues to evolve in 2020 with advancement in technology like Apache Flink for real-time stream processing and Kubernetes for container orchestration. The concept of the data lake, a centralized repository for storing structured and unstructured data at any scale, gained traction. One of the factors that contribute to the development of big data is technological advancement. The decreasing cost of storage solutions such as cloud storage and distributed file systems make it more affordable to store large volumes of data. Advance in hardware technology, including more powerful processors and increased storage capacity, have enabled the processing and storage of vast amounts of data. Data processing frameworks like Apache Hadoop and Apache Spark provide scalable and distributed computing capabilities, which will make it easier to process and analyze big data. Next factor is data governance and security. As data becomes more valuable, issues of governance, privacy, and security becomes critical. The development of robust data governance policies and security measures is essential for the responsible use of big data. Another factor is regulatory environment. Compliance with data protection and privacy regulations such as GDPR and HIPAA has become a significant factor in the development and use of big data. Adhering to this regulation is important for maintaining trust and ethical data practice. The last factor is data processing analytics tool. For advanced analytics, the development of sophisticated analytics tools and algorithms will allow organizations to extract valuable insight from large data sets. Machine learning and AI technologies also play a crucial role in analyzing patterns, predicting trends, and automating decision-making process.
Big data is characterized by three V's, which are volume, velocity, and variety. These attributes distinguish big data from the traditional data set and highlight the uniqueness. The first one is a volume. Big data involves a massive amount of information. This can range from terabytes to petabytes and beyond. The sheer volume of a data is often one of the defining features of a big data, requiring specialized processing and storage solutions. Next is the velocity. Big data is generated and collected at unprecedented speed. The rate at which data is produced, processed, and analyzed is a crucial aspect. Real-time or near real-time processing is often necessary to extract a meaningful insight and a value from the rapidly changing data stream. Variety big data came in the diverse formats and types. It includes a structured data, unstructured data, and a semi-structured data. The variety of data sources and the format pose challenges in terms of integrations, analysis, but also offer opportunities for richer insight. Other than that, some formulations extend the characteristic to include the veracity. Veracity refers to the quality of data. Big data may include the inaccurate, inconsistent, and errors. Ensuring the data accuracy and reliability is crucial for meaningful analysis and decision making.
Next, I will explain on the advantages of big data in accounting profession. First is cost reduction. Big data analytics can uncover cost-saving opportunities for organizations. Automation of routine tasks through big data technologies can lead to significant cost savings for accounting firms. This allows accountants to focus on more complex tasks that require human judgment and analysis.
This is not only save time but also enhance cost efficiency by minimizing the risk of errors and allowing accountants to focus on more strategic tasks. By analyzing data related to operations, supply chains, and resource allocation, businesses can identify areas where costs can be minimized, such as optimizing inventory management or reducing energy consumption. Second advantage is innovation. Big data analytics enable accountants to analyze vast amounts of financial data quickly and uncover valuable insights. This information can be used for more informed decision making, allowing businesses to respond promptly to market trends, financial risks, and opportunities. It also fuels innovation by providing insights into market demands, customer preferences, and emerging trends. The organization can leverage these insights to develop new products, enhance existing ones, and align their offerings with evolving customer needs. By analyzing historical financial data, big data tools can help accountants make predictions and forecast about future trends, enabling businesses to plan and strategize effectively. Third is enhanced customer service. Big data analytics enables organizations to understand their customers at a deeper level. By analyzing customer data, businesses can identify preferences, behaviors, and needs, allowing them to personalize products, services, and marketing campaigns to enhance the customer experience. It also enables accountants to analyze vast amounts of financial data quickly and uncover valuable insights. This information can be used for more informed decision making, allowing businesses to respond promptly to market trends, financial risks, and opportunities. There are three disadvantages of big data in accounting profession. First is data quality and reliability. Big data poses challenges related to data quality and reliability. The volume as well as a variety of data sources can lead to issues such as incomplete or inconsistent data, which may affect the accuracy and validity of analysis if not properly managed. Big data analytics can introduce biases in the decision-making process. Biases may arise from the data itself, the algorithm used, or the interpretation of results, leading to unfair or inaccurate outcomes. Second is ethical consideration. Big data analytics often rely on algorithms to make predictions and decisions. If the historical data used to train these algorithms contains biases, the outcomes may perpetuate or exacerbate existing inequalities. This raises ethical concerns about fairness and impartiality. The complex nature of big data analytics means that an unintended consequence may arise. Ethical considerations require ongoing monitoring to identify and address any unintended negative impacts on individuals or groups. It often involves the collection and analysis of vast amounts of personal and financial information. This raises concerns about the privacy of individuals as the data may include sensitive details that if misused can compromise confidentiality. Third is high implementation maintenance costs. Implementation of big data solutions can be costly for organizations. Investment in infrastructure, technology, and skilled personnel are required, which may pose challenges, especially for small and medium-sized businesses. Big data systems require ongoing maintenance, updates, and improvements. Keeping the technology up to date with the latest features, security patches, and performance enhancements is an ongoing cost. Ensuring the security of sensitive financial data is a top priority. Implementing a robust cybersecurity measures, encryption, access controls, and compliance with data protection regulation incur additional costs. The case that we have chosen is storage capacity prediction using population analytics. The document discusses the challenges in accurately predicting storage system capacity usage and proposes a new prediction method based on population analytics. It points out the limitations of traditional prediction methods, which rely solely on historical usage trends and do not perform well when storage usage does not follow historical patterns, such as during system deployment or benchmarking. The paper also discusses the prediction approach for non-standard usage patterns and the selection of the best prediction approach based on historical accuracy. The evaluation demonstrates that the proposed approach improves the capacity prediction for a majority of the systems and effectively addresses the limitations of traditional prediction methods. In conclusion, The document presents a new capacity prediction method based on population analytics, which effectively addresses the challenges of traditional prediction methods. It leverages common usage phases across storage systems and adjusts predictions based on the current phase, resulting in significant improvement in prediction accuracy, especially for non-standard systems. The proposed method has the potential to enhance the prediction capability of various popular prediction techniques in the future.
Based on the challenges from the case that has been extracted by Hazira just now, the article proposed a prediction technique based on the insight that the storage system usage trend can be categorized into several phases like deployment, growth, and steady usage. The capacity prediction depends on the storage system's current and future phase. Their technique modifies the prediction from the underlying prediction methods based on the current phase of the given storage systems, as it determines the extent of influence the more recent or older data can have on the prediction according to its current phase. Usually, some systems do not show the standard usage pattern marked by distinct phases. For such systems, their technique automatically switches to the approach with the most accurate historical accuracy to improve the future predictions. To measure predictability, they leverage a combination of performance, capacity, and configuration metrics, where multiple metrics are better indicators to triangulate storage systems' unpredictable behavior, like during benchmarking.
As what have been presented earlier by other previous presenters, have you wondered what is the relationship between big data and cloud computing? So, big data is actually the large data set collected from large network-based systems, whereas the cloud is the location that this data is processed and accessed, usually using a software-as-a-service model and utilizing AI and machine learning to present the data to its users. So, big data and cloud computing have a symbiotic relationship as the cloud infrastructure effectively enables storage, real-time processing, and big data analysis at scale and quickly. So, the biggest benefit of using cloud storage for your big data is the scalability, where cloud storage is available on a pay-as-you-go basis. Essentially, the cloud is the mechanism that serves, stores, and presents the opportunity for users to access and analyze big data efficiently. Hence, without cloud computing, there would be a huge amount of untapped potential within big data analytics, as current computers cannot analyze the scale of data feasibly, if at all. At the same time, big data plays a huge role in the development of cloud computing because without big data, there would not be anywhere near as much demand for cloud-based solutions. So really, cloud computing services exist because of big data. The only reason we collect big data is that we now have the services capable of collecting, storing, and processing the data. So simply, one would not exist without the other. A combination of these two can transform the organization into an efficient, data-driven market leader.
In conclusion, accountant can greatly benefit from cloud computing, streamlining their tasks and reducing the operational expenses significantly. Additionally, the vast potential of big data presents an opportunity for accountants to enhance the organization value and help the businesses leverage their large dataset. We are optimistic that the adoption of these emerging technologies will enhance accounting efficiency and pave the way for promising the future in the profession.